Hello students, we'll discuss properties of pyrrole today. Pyrrole is a colorless liquid having boiling point 404 Kelvin. It turns brown on exposure to air, otherwise it is colorless. It has chloroform like odor. It is sparingly soluble in water but fairly soluble in alcohol and ether. It is considerably aromatic in character, which is marked by its ability to exhibit electrophilic substitution reactions. Other reactions are also shown by it. It shows electrophilic substitution reactions, acidic character, basic character, reduction, oxidation. Ring can be expanded, reaction with malic anhydride, and ring cleavage reaction. About electrophilic substitution reactions, as in case of benzene, it also shows electrophilic substitution reactions. But pyrrole is more reactive towards electrophilic substitution reaction. It resembles activated benzene derivatives like aniline and phenol in its reactivity towards electrophilic substitution reactions. All electrophilic substitution reactions take place at second position of pyrrole, or this may be called alpha position. If both the alpha positions are occupied, then the substitution may take place at beta or third position. Its greater reactivity towards electrophilic substitution may be attributed to greater electron density on pyrrole ring in comparison to benzene. In benzene, 6 pi electrons, these are on 6 carbons, whereas 6 pi electrons are on 5 atoms. So pyrrole is having greater electron density in comparison to benzene. Accordingly, reactivity towards electrophilic substitution reactions of pyrrole is greater. About mechanism of electrophilic substitution reaction in pyrrole, first step is generation of electrophile. If Ez is some species, it dissociates to give E plus and Z negative. E plus is electrophile, and this electrophile in second step, attack of electrophile, attacks at pyrrole ring to give substituted pyrrole carbocation, and this is when electron shift from this to this place, alpha position. Electrophile can attack at this alpha position. Accordingly, when electrons have shifted from this to third to second position, there is positive charge on third position, means carbocation is formed, and this carbocation is stabilized by resonance. This electron pair when moves here, double bond is here, and the positive charge in turn comes here at this position. Again, another resonating structure in which the positive charge is accommodated by nitrogen. This electron pair when shifts here, nitrogen occupies positive charge, and this structure in which nitrogen is having positive charge is specially stabilized structure, because here in this structure every atom that is having complete octet. The third step is removal of proton. This carbocation, when attacked by Z negative, it abstracts a proton from here, giving HZ species and furnishing substituted alpha position is substituted, alpha position hydrogen is substituted by electrophile, E substituted pyrrole is obtained. Now we have seen that this electrophile gets substituted at second position, and in second position we saw in 3 resonating structures the third structure was specially stabilized because every atom was having complete octet of electrons. In case the attack takes place at position third, attack of electrophile. For this attack to take place at position third, the electron density has to be greater on position third. This electron pair shifts here, third position. Electrophile gets substituted and carbocation is formed, the positive charge on second number carbon. When this electron pair present on nitrogen shifts here, the positive charge is there at nitrogen. Only 2 resonating structures are here, 4 and 5. In case attack took place at position 2, first, second and third. First, second and third, 3 resonating structures were there. Because attack at position 2 yields a carbocation which is resonating structure, which is having 3 resonating structure, it is more stabilized in comparison to the attack when takes place at position third, where only 2 structures 4 and 5 are possible. Hence, position 2 is preferred position where the substitution usually takes place. Now about summary of electrophilic substitution reactions of pyrrole. Pyrrole, when treated with nitroacetate and acetic anhydride at 278 Kelvin temperature, 2-nitropyrrole is formed. About sulfonation, pyrrole treated with sulfur trioxide in pyridine at 373 Kelvin. Pyrrole 2-sulfonic acid is formed. Here we can see in nitration and sulfonation, no nitric acid, no sulfuric acid is there. Strongly acidic condition in both the cases are avoided, because in strongly acidic condition, pyrrole gets polymerized. Polymer of pyrrole is formed. Hence, no strong acidic conditions are employed here. Pyrrole, when treated with iodine in presence of Ki, 2, 3, 4, 5 tetraiodopyrrole is formed. Similarly, when treated with sulfonyl chloride in ether at 273 Kelvin temperature, 2, 3, 4, 5 tetrachloropyrrole is formed. And when with bromine in ethanol at 273 Kelvin, 2345 tetrabromopyrrole is formed. In all the three cases, iodination, chlorination and bromination, tetra substituted derivatives are formed. When treated with acetic anhydride in presence of stannic chloride, which acts as Lewis acid, it is weak Lewis acid, acetyl group gets substituted at position number 2. This is Friedel-Crafts acylation. 2-acetyl pyrrole is formed. When treated with chloroform in alkaline medium in presence of KOH or NaOH, aldehyde group, formyl group CHO is introduced at position 2. This is called Riemer-Tiemann reaction. And when treated with diazonium salts, this second position get occupied by the diaryl azo group, diazo group, and when treated with HCN, HCl and water, here also the formyl group gets substituted at second position. This is Getterman-Koch synthesis. All these were electrophilic substitution reactions of pyrrole. Second is acidic character of pyrrole. It is weakly acidic, and when treated with some alkali, this hydrogen, which is acidic one, gets substituted by alkali metal. The reason for its acidic character is the stability of anion substituted with it. The stability associated with pyrrole anion. This is pyrrole anion. We can see resonating structures of pyrrole anion. Negative charge here, in this structure, negative charges here at position 3, negative charge at position 5, and negative charge at position 2. No positive charge in any of the structure is there, means no charge separation is there in any of the structures. As none of the structures is involving charge separation, so the pyrrole anion is better stabilized by resonance in comparison to pyrrole itself, where we could see charge separation. Third property is its basic character. Basic character of pyrrole was possible if the heteroatom, which was having lone pair of electrons, were available for donation to some other species. Here, the pi electrons, the lone pair of electrons available on heteroatom, these are contributed towards delocalized pi electron cloud. As a result, pyrrole does not have any lone pair of electron on nitrogen, therefore it does not possess significant basic character. Next property, reduction. When reduced with zinc and acetic acid, one double bond gets saturated and 3-pyrrole is formed. And when reduced catalytically, treated with hydrogen in presence of platinum at 473 Kelvin temperature, both the double bonds get saturated and pyrrolidine is formed. Fifth, oxidation. Oxidation of pyrrole with chromium trioxide in acetic acid, malic imide is formed. Malic acid is COOH, COOH, and imide of this malic acid is malic imide. Next, sixth property, ring expansion. Pyrrole ring, which is 5-membered, can be expanded to 6-membered. Derivative of pyridine is formed here. 3-chloropyridine is formed when lithium salt of pyrrole, this is treated with chloroform. A bicyclic species is formed when this electron pair shifts here and this here, one chloride ion is expelled and 6-membered ring, pyridine ring is formed. 1, 2, at 3 position chlorine is there, 3-chloropyridine is formed. Next property, 7th one, reaction with malic anhydride. This is malic anhydride. Here, when malic anhydride reacts with pyrrole, substitution product is formed. At second position, H is substituted with succinic acid. Pyrrole 2-succinic acid is formed. About 8th reaction of ring cleavage. The ring of pyrrole is cleaved when it is treated with hydroxynamine hydrochloride, succinaldehyde dioxime, C double bond NOH, C double bond NOH. Succinaldehyde dioxime is formed. Succinaldehyde is, this is, if there is COH, succinic acid is there, and CH2, this is succinaldehyde, and when this aldehyde, this is treated with hydroxylamine oxime is formed here at these two places. Oxime is there, so it is succinaldehyde dioxime. That's all with the properties of pyrrole.